Hello, Annabella.
Hello,
Hello. Hello, how are you today? And that's for everybody as well.
I'm good.
Good, good, good. Me too. Me too. Me too. Okay, so admit. So just people coming in. There's still people coming through. So letting you all in. Okay. All right. I'll tell you what I'll do first is I've got just a few questions for all of you. And first things first, say thank you for coming in. Hello from South Wales in the UK. Hello and thank you for coming. Hopefully you'll get something out of this session. But the first thing I wanted to do was just to ask you a quick couple of questions here with you, just for you, so that I've got an idea really of where we are with knowledge and how to properly go about talking to all of you or talking with all of you. So here we go. Grade 10, good. Grade 10. Grade 10. A little, okay. Well done for coming. Grade 6. You'll be going up to secondary school next year then, after the summer. Okay, right then. Okay, well, if you just to get things started, we've never met before, we've never spoken before. Now, my big thing is I have a tendency to talk really quickly when I get going. So please do feel free to tell me that I'm talking too fast or too slow. Is how I'm talking now okay for you all?
No, it's okay.
Yeah, cool. Okay, good. Yeah, my name is Mark. As you can see, you can call me Mr. Mark or Mark or whichever you like, whichever's easiest for you. I've been working with Miss Lewis since 2013, 2014. I graduated from university in 1992, so that was 30 years ago. And I did environmental science at university. And I studied environmental chemistry. I've got 5 years teaching experience in the classroom, actual science, up through secondary school. And as I said, I've been working online since about 2013, 2014. So yeah, that's a little bit about me. And I'm based in South Wales at the moment. So about, I think, 3,000 miles, 4,000 miles, or from where you are, all the way across on the other side of the Atlantic Ocean is where I am, across the pond, as they call it, over here. Okay, so have a quick look at the polls, what we're doing here. So what we're looking at then is we've got a wide range. We've got grade 8, grade 10, and not very familiar, and you know a little about climate change and a little bit about the carbon cycle. Okay, all right. I'm going to upload what we're going to do in a minute. Anytime, feel free to ask questions anytime. It's an open session, this is. So anytime you don't understand something, please do shout, please do ask. And I'll do my best to answer the question. The first thing to say, of course, is it's a huge subject, and hopefully you'll, as I said, you'll learn something from this, and you'll have interest on it as well. So I'm also not very familiar with Zoom. I'm still getting used to it, which is why Miss Lewis is here to jump in if there's any technical issues. All right, okay then. So let's get the lesson up and running, and let's go. Okay. So here we are then. Here is the title. Okay. Any questions on that? Please contact the student shed. I just thought very quickly. That's what we're going to look at today. So don't sort of think that it's too much or anything like that. So we can see now, for some of you that are in grade 6 and in grade 7 and in grade 8, there's some pictures of equations and there's pictures of molecules and things like that in here. You don't have to worry about that right away, because you don't really start to have to worry about things like chemical equations until you get to really they come up in year 9 in grade 9. But you don't really need to get properly involved in that until you're in year 10. I love your color. I love your covers, Annabelle. It's great. Okay, so here we are then. So that's what we're going to look at today. So the next thing we're going to look at then is carbon. And what carbon is what we call a non-metal. It's in what's called the periodic table, where all the chemical elements are organized. It has 2 main forms, diamond and graphite. The hyperlinks are there for you to look at as well. It makes up, it's a time in terms of how much in the crust of the Earth, how much it takes up. It's less than 1/4% of the Earth's crust. But in nature, there's more compounds containing carbon than all the other elements that there are, than with all the other elements that they are combined. And the reasons for that are going to get explained now. So that's where it is. This is what's called the periodic table. So you can see it's here. What sometimes it's called group 4, or sometimes group 14. It's in here because this is one of those things you don't need to worry about quite if you're in lower grades, in 7 or 8. It's in group 2, in period 2, because it's got 2 shells where the electrons are in the atom, and it's in group 4 because it's got 4 electrons in its outer shell or its orbital, because that's where the electrons are organized. When you do the structure of the atom, that comes clearer. Carbon again, it exists in several forms called isotopes. The form of carbon we're looking at has got 6 particles called neutrons and 6 particles called protons in the neutrons in the nucleus, 6 electrons in its atom, 2 in the first shell, 4 in the second. And this is really important, where there's this idea that it's got these 4 electrons in the outer shell, because this means it can form, each carbon atom can form what's called, can form 4 covalent bonds. Now the bonds, that's bonding between non-metals, and the way that it bonds, it can form with other carbon atoms, or with hydrogen, oxygen, nitrogen, and sulfur. And there's not very many other elements that can do that. But the result is that although there's not much of it in the ground, there's millions of different compounds which contain carbon. And those compounds can be what's called inorganic or organic. So yeah, there's a picture of carbon there for you to see how the electrons are organized. So we said this is the first shell where there's 2, this is the second shell where there's 4, and it's these 4 electrons that are important for chemical bonding. Okay, we mentioned this word organic. A carbon molecule will be organic if it has at least 1 carbon-hydrogen bond in it. All the other ones, there we are, all the other forms of carbon are said to be inorganic. But the interesting thing for us, for this, is that the other carbon is one of the elements of life. The other ones are these are the symbols of those elements are hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Now, in science, we put all of these together and we call them what's called the CHNOPS elements, and they're called the elements of life. And underneath here is just a little link here. If you go on here when we're done with this, you'll get a link to the University of Nottingham, and which is a city in central England, and they've built a periodic table with lots of videos in about how the different the properties of all the different elements. The main fella in there's got huge hair, great big hair, and so yeah, he's called Mr. Hairman. But anyway, okay, so what the main molecule we're going to be looking at today is carbon dioxide. Carbon forms 2 oxides. One's called carbon monoxide, the other one's called carbon dioxide. Both of these are inorganic molecules, and carbon dioxide is by far the most important. For what we're going to be looking at today. It's crucial. It's a linear molecule, which means it's just got a long shape. And as you can see from here, the carbon atom forms 2 double bonds with an oxygen with an oxygen atom. Remember how we said it can form 4 bonds? Well, in carbon dioxide, each carbon atom forms 2 bonds with an oxygen atom. So 2 plus 2 equals 4, and that's how you get carbon dioxide forming in other molecule forms. Okay, so carbon dioxide is a colorless, odorless gas. It's soluble in alcohol and water. This is some of the properties of it. But the crucial thing about this is where it comes from and how it impacts in this thing called the carbon cycle that we're going to be looking at today. It's produced in combustion reactions when in an excess of oxygen. It's produced when what's called carbonate rocks are heated by thermal decomposition and by the action of acids and acids on carbonates and carbonate rocks. These are what's called non-biological or abiotic sources of carbon. But the crucial thing with this is the link that there is with the natural world with carbon dioxide, because it's essential for photosynthesis. Now, you've all heard photosynthesis before. Is that right?
Yes, sir.
Yes. Good. You've all heard of that before. Okay, so it's the most studied reaction in the world. We'll see why. You'll find out why that is during the course of you go through of your courses. Okay, so but it's in the atmosphere, tiny amount, 0.04%. And where part of the reason for that is because plants absorb it. And an autotroph here is just a fancy word for plant. Like an algae, a plant, the trees, the seaweed that you can see on the island that you live. An autotroph is just an organism that makes its own food. That's all it means. And the reason and the way that it can do it is through photosynthesis. Now, the opposite of photosynthesis, if you like, is a process called respiration. And that releases carbon dioxide to the atmosphere. So what you have here is a movement, or a fancy word for saying that is a flux of carbon dioxide between what's called the abiotic and the biotic environment. So what that means is there's a movement of carbon dioxide between what's alive and what isn't. Okay, and so what we say with this is that carbon dioxide is the fixable or useful or movable form of carbon in the atmosphere, in the planet. Here we are, and you will have to learn this equation: photosynthesis and respiration. And photosynthesis is the main biological mechanism by which CO2 is removed from the atmosphere. And respiration is the main one by where it is released to the atmosphere. So in a way, if you can look at the equation, you can see, moving around too much, sorry, you can see that carbon dioxide is being taken in, and with respiration, carbon dioxide is being given out. All right, so one comes in, one comes out into plants and animals for us. Okay, so carbon dioxide as well exists in rocks in the form of what's called carbonate rocks. We've mentioned them already, in calcium carbonate, calcium magnesium carbonate, and copper carbonate. Now these are why I picked these ones, because most of these you're going to come across in the laboratory. You'll see them. You'll do various experiments with carbonate rocks in your chemistry classes. We call them a carbonate because a carbonate is any substance which contains this ion. If it contains that ion inside it, it's a carbonate. And carbonate rocks are also good examples of what's called a sedimentary rock. Which is, again, as I said, the hyperlinks are there for you to look at later on. A sedimentary rock just means a rock that's formed when the substance is layered down on the earth, in the ground. But in the laboratory and in nature, carbonate rocks are broken down by heat. What this always does is produce an oxide of the metal and carbon dioxide gas. And in acids, carbonates also break down as well. So your sulfuric acid, your hydrochloric acid, your nitric acid, the acids that you would have seen and heard in your classrooms in school. And whenever you get carbonates and acid coming together, reacting together, sorry, you always get what's called a salt, a water, and carbon dioxide. And along with combustion, things being burnt, these are all of these are sources of carbon dioxide to the atmosphere. So what we're trying to say here is that we've got all some from these various different sources, biological, living and non-living. There's a flow of carbon dioxide into the atmosphere. But the question now is what happens to that carbon dioxide when it's in the atmosphere? Okay, so but here's what's called the thermal decomposition of carbonate. So what you notice, what do we notice about that? Just a quick question for anybody. What do you notice about the equation here?
That they all add CO2.
Yeah, they all produce CO2. This is the whole point. This is they all produce CO2. So so they all produce CO2. So that's I'll start that again. It's me talking too quickly again, slowing down. They all produce CO2, and you also get this other substance here called the oxide of the carbonate. So you have the carbonate here, heat it, you get an oxide, and you always get carbon dioxide. It always happens. So yeah, well done, well noticed. You also have the same thing happens with acids. Oops, I'll keep that still there. So you have the carbonate here. You put in this case, it's hydrochloric acid, substance called hydrochloric acid. You get sodium chloride, water, and carbon dioxide. Again, every time you get a metal carbonate and acid, you always get carbon dioxide. So I don't know if you've seen any film of what's called acid rain. When that falls on things like limestone or metals before it starts to fizz and bubble, what's happening there is you're getting the salt form and you're getting carbon dioxide released into the atmosphere as well. So yeah, so that's just an introduction there of some of the basic chemistry of what happens with it. You also have in combustion reactions. Now we've got a fire here in the house. We haven't got central heating on at the moment, but what we have got is a little fire. It's still cold here, you see, and we've got a combustion reaction going on at the moment as well, which will be working. This is what will be happening. We'll be producing carbon dioxide and water in the fire that we're using to heat our house. In the natural world, whenever you have anything that contains carbon in it, you burn it in oxygen, you combust it in oxygen, you're always going to get carbon dioxide. And if there's not enough oxygen, you get carbon monoxide. Okay, right, now we're getting into beginning to see where it all came from. So fossil fuels, which is what we're going to be talking about today, is removed from the carbon cycle long time ago, millions of years ago, and their combustion today is pumping it back into the cycle, into the carbon cycle. I'm going to come to show you a picture of that in a minute. So over millions of years, you have how coal was formed, and over millions of years you have how oil was formed. The big difference is that coal comes from plants and oil comes from animals, okay, from the sea, in the sea. Okay, so another natural source is the breakdown of anything organic in the garden, in the ground, also releases carbon dioxide and methane to the atmosphere. And if you have no oxygen present, you get methane released to the atmosphere in what's called anaerobic. That's just, again, that's just a fancy word of saying that their way of saying there's no oxygen. Aerobic means in the presence of oxygen as well. So aerobic means there is oxygen. Anaerobic means there is no oxygen. Okay, so in all of everything we've seen here, all of these processes, carbon atoms in the form of carbon dioxide are moved between the living and non-living parts of the environment. The reason it works this way is because carbon dioxide is the form of carbon which is useful to organisms, useful for photosynthesis. So what we're saying is that the production and movement of carbon dioxide through the abiotic and the biotic environment is essential for life on Earth. But what does that mean? What does that mean? What we mean by the external environment is everything around us. The internal environment means inside you, and organisms and their external environment always interact with each other. And we break this down into, I've used the word already, into biotic and abiotic factors. And what this does is that this means that we bring it all together. The natural world and the living world and the non-living world interact with each other by means of biology, chemistry, and geology. And that's where the word biogeochemical cycle comes from. So what this means is these are the pathways where all of these substances are moved through the Earth. Okay, so, and there's a quick slide here to show you biotic, abiotic, and the point is that they interact with each other, and when if things change in some way, then there's consequences and knock-on effects for the biotic and abiotic world. That means so there's consequences for life and for the planet. Okay, so what is this thing called the carbon cycle we're talking about? What it means it's the movement of carbon and the compounds which contain it. It is an example of what we call a biogeochemical cycle. All the other elements, the Cheops elements we mentioned, are moved by their own cycles. So there's a sulfur cycle, a phosphorus cycle, an oxygen cycle, and so on. And they move material and energy in the form of chemical compounds. And they move them between the living, the biotic, and the abiotic environment. And the cycling has to be constant and in balance, because if it isn't in balance, you've got problems, which is what we're going to be looking at as well. So there they are. There's some of the ones that are mentioned: the carbon cycle, the phosphorus cycle, nitrogen cycle, water cycle, and the oxygen cycle. The GCSE, you only and up until A level as well. You're just going to be looking at the nitrogen cycle and the carbon cycle. But the other ones are just as important, and you study them later. So what they do is they make the planet work. They drive all the interactions that you see around you, all the things you'll hear about in biology and chemistry. They make the planet work properly. So they drive all the interactions which happen between the cycles and inside them too. Okay, right. The movement can be in any of the states of matter. In carbon, so that's solid, liquid, or gas. With the carbon cycle, it's carbon dioxide. And so what a biogeochemical cycle is the movement of any chemical element and/or the compounds which contain that element. Just as a general, cycling in the abiotic environment takes much longer than in the biotic environment. You'll sometimes see when you look at the different cycles, you'll get the slow carbon cycle or the fast carbon cycle. The slow carbon cycle is to do with anything that isn't alive, and the fast carbon cycle is to do with living organisms. So here it is. Now, the key thing with all of this is to see, you see up here, it says process and reservoir. So photosynthesis and respiration are what's called processes, because that's where something's actually happening. But a reservoir might be the ocean, the ground, the plants, and the animals. So it's a movement by processes between reservoirs, and the reservoirs can be living or they can be non-living, abiotic or biotic. So it's a movement. The carbon cycle moves atoms of carbon in the form of carbon dioxide between the living and the non-living parts of planet Earth. Carbon flows between each reservoir in an exchange called the carbon cycle. Now you can see, looking at the image there, it's a huge subject. We're not going to cover all of this today. We're not going to go through all the different parts of it today. It can't be done in one lesson, not properly at any rate. So we're going to overview some parts of it. But it's this idea that you have processes, and those of you, I think even in grade 6, grade 7, you cover things like diffusion, and you've heard these words: respiration, photosynthesis, and such like before. Burning. These are all processes which move carbon dioxide, which move carbon, produce carbon dioxide through the different reservoirs, so which can be living and non-living, and they can be in the land, and they can be in the sea, and they can be in the air. Yeah. So the source, is everybody happy with that? Is there any questions at all? Everyone all right so far? Anybody got anything to add or say or contribute? We all good?
Yes, sir.
Good. Okay, right. Okay then, so the source of all the carbon in the biota, the living world, is carbon dioxide. It's in the atmosphere or it's dissolved in water. Photosynthesis is the primary method, the main way that carbon dioxide is used. It comes from the atmosphere, and it comes from the soil, and in the equation, and it's converted into simple carbohydrates, what we call simple carbohydrates, like glucose. And here's the equation again. So we have this idea that the sun hits the leaves, drives it all. The carbon dioxide is taken in to the stomata, and in combination with water from the soil, water, carbon dioxide, sunlight produces glucose and oxygen. Okay. So the trees take in the carbon dioxide, use it to drive their own life processes, and produce oxygen as a waste product, which we breathe. Okay, so it's important to realize that the oxygen that we're breathing now hasn't always been on the Earth. The evolution of photosynthesis hasn't always been on the Earth. Photosynthesis actually came onto the scene about 3 billion years ago. So the most of the oxygen that the oxygen that we're all breathing, that all animals breathe now, is billions of years old. It wasn't always here. Photosynthesis is an evolved process, but we'll do that another time. Okay, so the glucose is used to drive respiration, or is converted into more complex carbohydrates called polysaccharides, like starch, fiber, or cellulose. And there's just a schematic I wanted to put in here about why plants need glucose. I thought this would be a really good general slide to have for you to be able to see why do plants need glucose. It's not they don't just use it for to drive respiration, drive their energy. It's used as a building block for all kinds of other chemicals as well. Okay, and so I thought that would be a good way to explain the importance of the glucose molecule. Okay, so this is for those of you that are in this is the sort of thing. Don't panic when you see structures like this. You don't have to remember anything like this, and you'll never ever be expected to draw it or anything like that. And if you're not doing GCSE at the moment, don't worry about some of these words, and don't worry about the images. What we're saying is that in the plants and the animals, the glucose can build up together by reactions which are called condensation reactions into long chains. But these chains can also be broken down by what's called hydrolysis reactions. So what happens is, if you think about an organism like a tree, or the kelp in the ocean, say, more complex molecules are a biological mechanism by which carbon is stored in the land and in the sea. But terrestrial is on the land, marine is in the sea. Now, the stored products which make up the organism can then be eaten as food by consumer organisms. So that means everything that isn't plants. And what can also, or the organism, like it is a tree, can be converted into a carbon reservoir, such as the carbonate rocks we've been talking about. Coal, peat, oil, and natural gas are all there. So what this means is, if you have this idea, if you've seen pictures like this before, I think even in grade 6 you would have seen something like that in ecology, these sorts of pictures before. Yeah. I thought so. So what happens is, when we had this word autotroph, that means your plants that make their own food. All other animals are called heterotrophs, and they eat the producers. So what this picture is here for is to show is that the producers, that's the plants and the algae, act as sources of essential substances for all other organisms. So without the plants, then there is no us. There is no ecology, because they form the basis of ecology and biology on the Earth. Respiration and metabolism produce carbon dioxide, and it moves upwards through the food chain. But all of it is driven by the sun. Okay, so it provides the energy for all of this. Okay, so in the carbon cycle, atmospheric CO2, that just means the carbon dioxide in the atmosphere is captured by the autotrophs. That means the plants. Some of it is converted to glucose, which is an energy source and a building block. And some carbon dioxide is converted to more complex molecules and stored, so your starches and your fibers and such like. The forests, the world's forests, are a really good example of a carbon sink. Heterotrophs, that just means animals, consume autotrophs, that's the plants that we eat, and the organic compounds pass through food chains and food webs. So they move up the food chain and through the food webs. And here we have a picture here. I just thought I'd show you this. And so, but what's happening here is global forest destruction and wildfires are a reason why forests are becoming sources of carbon dioxide to the atmosphere and not sinks. So what's beginning to happen is because we've chopped down so much forest, the planet is losing its ability to take carbon dioxide out of the atmosphere in enough to stop it building up. Now, last year, 2021, was a record year for wildfires on the planet. And in 2022, unfortunately, it looks like it's going to be even worse. Unfortunately, events I'm sure you've seen the news, events in Ukraine are going to make a lot of this a lot worse. But again, that's another story. So what happens then in the carbon cycle in the forest? You have the trees. Oops, sorry, here we go. Carbon uptake from the atmosphere in the form of carbon dioxide. Carbon can be released. Remember the combustion reactions that we talked about. So you get carbon dioxide into the atmosphere there. Carbon dioxide is released by decomposition, but it also can be stored in dead trees. And that's where the trees eventually become coal over millions of years. And of course, when trees grow again, carbon uptake and storage can lead to regrowth of the trees as well. So what happens is photosynthesis removes carbon dioxide from the atmosphere. Combustion, respiration, and decomposition produce it. They release carbon dioxide to the atmosphere. If more carbon dioxide is produced than is removed, the cycle is out of balance. And of course, the big problem, one of the many problems we're facing now, is that the world's forests now emit more carbon dioxide to the atmosphere than they remove, which is not really how things should be. It should actually be the opposite. But there we are. But another area of this to look at is the oceans. So I thought, I live on an island, you live on an island, so I thought, okay, we'll do something about how the oceans work with this. So the oceans remove carbon dioxide from the atmosphere. Now, remember how we said right at the start that carbon dioxide is soluble in water? When it dissolves in water, it forms a substance called carbonic acid, and that's one reason why rainwater is slightly acidic. Now, just as a general point, carbon dioxide is an example of what's called an acidic gas. Now, those of you that are doing GCSE starting off in year 10, little nugget of information for you is that all non-metal gaseous oxides are acidic gases. So that's things like carbon dioxide, nitrous oxide, sulfur dioxide, any one of those non-metal gases, all of them are non-metal gaseous are all acidic gases. And the reason that they're acidic gases is that when they dissolve in water, they liberate hydrogen. They produce hydrogen when they dissolve. And here we have it. So what you have here, this another equation here, is carbon dioxide and water produces hydrogen carbonate. And then all the way through, you get the carbonate ion, and produces hydrogen, which makes it acidic. Hydrogen carbonate, 2 hydrogen atoms, and the carbonate ion. The carbonate. This symbol just here means that the reaction is reversible, so it goes in both directions. Now this is crucially important. So you have in the ocean the carbonate ion and carbon dioxide, and all of this together is crucial for the ecology of the ocean, because what happens is what organisms called phytoplankton also remove carbon dioxide from the atmosphere, and they use it to drive photosynthesis as well. Shell building organisms, so like corals and so mollusks, corals, and tiny algae called, I can never say this, called coccolithoporids, I got it that time, use metal ions that's in combination with the carbonate ion. So the carbonate ion is here to form metal carbonates, such as calcium and magnesium carbonate. Now, these compounds are insoluble in water. Now, if you think about it, if you're a shell building organism and you make your shell, or imagine you make your bones outside, you imagine you had an exoskeleton, you wouldn't want your exoskeleton to be dissolving in the water, would you? Because you need it to hold on to protect what's inside the organism. So you see, because most carbonates are insoluble in water, but that changes if the solution, in this case the ocean that they're in, becomes more acidic. The pH decreases and the solution becomes more acidic. Okay, so what happens in the oceans then? You have calcium ions, 2 bicarbonate ions, which is these ones here, forms calcium carbonate, produces carbon dioxide and water. Okay, so that's what happens. That's how the process, the equation which represent the processes by which the sorts of organisms we mentioned here make calcium carbonate for themselves in the ocean. And they have enzymes and various biological processes which make the shell form or form the coral. But you always get calcium carbonate, which is here, carbon dioxide and water. Okay, so the calcium carbonate is in an acidic solution. Now you'd think maybe it would dissolve, but it doesn't. This is where it gets a little bit tricky. But the calcium carbonate, the shell, doesn't dissolve because the ocean is already saturated with as many calcium and carbonate ions as it can hold. So what's being said here is it's got nowhere to go. So it can stay on the organism. It can stay as the shell. It can stay as the coral. It can stay as the tiny little scales that there are on the small organisms. Now, as you go further down into the oceans, further deep down, there's a certain depth where the calcium carbonate does start to dissolve. And this is what's called the calcite compensation depth. And it's the point at which in the ocean, shell building organisms can't make their shells anymore because the chemistry of the ocean has changed. Now, this is a big problem because one of the consequences of climate change and one of the problems that there is in the oceans is what's called ocean acidification. Because of so much carbon dioxide has been released into the atmosphere, because we've chopped down so many forests, or so many forests have been chopped down, because we've had so many wildfires, we've actually created a situation now, or a situation has been created where there's so much carbon dioxide in the atmosphere that ever more and more and more of it is finding its way into the oceans. Now, what that means is that because it dissolves in water, it's an acidic gas, it's making the oceans more acidic. So what that is, the consequence of that is it's reducing what this calcite compensation depth. So it's reducing, bringing it closer to the surface, the depth at which this reaction can happen. And if this reaction doesn't happen, the organism can't make its shell, can't make its bones, can't make its scales. It can't function. Be like, imagine if you had, I don't know, let's say it was really, really hot where you are, really, really hot one day, and you had no shade at all, and you had no protection. Eventually you're just going to get really, really, really hot, aren't you? It's like over here, it's still winter over here and we still get rain. I have to go sometimes at the weekend, I have to go and work in the rain. And when I work in the rain, I have a waterproof on because it keeps me warm and dry, doesn't it? If I take the waterproof off, if I don't have a waterproof on, I'm not going to be able to do my job properly, work properly. It's the same kind of idea with this. If they haven't got, the organism can't manufacture calcium carbonate, make its shell, then it's going to be in trouble. It's not going to be able to develop and grow properly. So what ocean acidification has done is it's basically meant it's decreased what's called the CCD, the calcite compensation depth. The depth is moved towards the surface. This means that marine organisms, marine is just a fancy way of saying organisms which live in the sea, have less ocean in which to build their shells. Okay, so has anybody got any questions with that before we move on to the next bit? Everyone all right? Now, there is a recording of this, isn't there, as well? So yeah, okay then. So it's another equation here, and this is what is the way that it's expressed. Oh, sorry, I'll keep it still. There we are. Okay, so what happens is if the oceans become acidic, the reaction moves to the right. In chemistry, as you get to GCSE, as you'll do equilibrium in reversible reactions. In the arrow here, it moves to the right. It means you get more calcium in the ocean and more hydrogen carbonate in the ocean and less calcium carbonate, which is really what the reduction of what happens underneath the calcite compensation depth. Okay, so the dissolution of the dissolving of calcium carbonate at reduced depths in the oceans is having a really bad effect on the chemistry and so the ecology of the oceans, because a lot of the organisms that are being affected by this are the ones at the bottom of the food chain. They're the producers, or they're small microorganisms which are food for the rest of the food chain and the rest of the food web. So if you haven't got food produced at the bottom of your food chain or the bottom end of your food web, that begins to break down. The rest of the ecology of the ocean begins to break down as well. And I guess the obvious example maybe to use with that one would be the blue whale. Biggest organism on the earth, biggest animal on the earth, eats the smallest. And so where there's a serious concern that they could be in trouble because they've got nothing to eat because of the breakdown here. Okay, and this is just another picture here which just shows it really. So above it you get what's called calcareous oozes formed. Below it you get the complete dissolution of carbonate ions. So above the line you get formation of calcium carbonate. below it, you don't. So, and you can see that the average depth is 4.5 kilometers down. Shallow waters are more favorable for calcium carbonate than for deeper regions, sorry, in the ocean. So yeah, so that's a very simple diagram there just to show you when and where it happens in the oceans. Okay, so the largest carbon sink is the crust itself, what's called the lithosphere. All those carbonate rocks, so your magnesium carbonate, calcium carbonate, about 70,000 billion tons worth. That's a huge number. So it makes up a huge amount of the Earth. So when these rocks are heated during volcanic eruptions, huge amounts of CO2 are released into the atmosphere. And when these eruptions happen, it can have massive impact on how the planet works. And we don't really see that many volcanic eruptions now, but back in the deep past there were. 250 million years ago, there was a sustained period of volcanism which lasted between 2 and 5 million years. And it was this, and I learned about this at university. That was me hooked on all things to do with climate and mass extinctions and how the planet works and what we're doing to the Earth and what's actually happening to the Earth itself. But this event called the Permian mass extinction started about 250 million years ago, lasted for between 2 and 5 million years. Can you imagine that? Volcanoes on the way for 2 to 5 million years. I can't even think about what happened yesterday or last year for that. Can you imagine? And volcanoes over all of this area. That's an area the size of Europe at least, and it going for millions of years. When this happened, it kickstarted a whole series of events, which came to be known as the Permian mass extinction, otherwise called the Great Dying. And for good reason, this mass extinction is referred to as wipeout, or the day the Earth nearly died, because over the course of about 100,000 years, almost everything was wiped out. And the thing is, with climate and what's happened to the planet at the moment, this is the kind of territory, unfortunately, that we are heading into. So that's what turned me on, got me hooked, and got me going on, got me interested in all of this, and I've been following it ever since. So we've said, though, in the oceans, calcium carbonate is made of calcifying organisms, corals. After the organisms die, they sink to the seafloor in the ooze that we talked about here, that there is here. That's what happens in the seafloor, and it gradually gets crushed over time, and it becomes sedimented and cemented into carbonate rock, and it gets stored in the form of limestone. And about 80% of the Earth's 80% of the Earth's calcium carbonate is made in this way, and it's this that gets released into the atmosphere in the volcanic eruptions. So a very, very, very simple diagram I put there for you. You can see it heats the rocks, carbon dioxide into the atmosphere. With volcanoes, you also get other acidic gases, sulfur dioxide, nitrogen dioxide, and such like as well. But this is the crucial point. So when people say things like, oh no, what they think the way that human beings operate doesn't really affect things very much, it's just not true. It really, really isn't. Volcanoes emit about 400 million tons of carbon dioxide to the atmosphere every year. Ourselves, human beings, is something like 30 billion tons and rising every single year into the atmosphere. So that's what we're doing, is releasing about 100 times more carbon dioxide into the atmosphere than what the natural world does. And that's going on and that's happening every year. So what happens with it is the extra carbon dioxide stays in the atmosphere, and that doesn't get transported or accumulates. And it's that which causes climate change. But it's also the accumulation of the carbon dioxide in the atmosphere, which means it also gets moved into the oceans as well, causing the ocean acidification that we've just been talking about. Yeah, and it's another quick diagram here which just shows you the movement of carbon dioxide through the abiotic environment. So it comes out of the volcanoes into the atmosphere, gets dissolved in the rain, washes through the rain, weathers the rocks into the sea, and you get the formation of calcium carbonate into the formation of calcium and hydrogen carbonate into calcium carbonate, gets turned into rock, calcium carbonate and other carbonate rocks, and the volcanoes release it gets heated, and the volcanoes release it into the atmosphere. And there you go, and it just goes round and round and round. And that's a cycle that's been going on really since the Earth formed. So it's a pivotal part of how the Earth works. Main biological source of carbon dioxide to the atmosphere is respiration. The main human-induced source is fossil fuel combustion, and the main natural abiotic source is the thermal decomposition of carbonate rocks. And the decomposition happens in volcanic eruptions. It also happens in cement manufacture, which is part of the carbon cycle called the limestone cycle. There's a hyperlink there which explains that in more detail. There's also a lesson that I put together on on the manufacture of limestone and the manufacture of cement as well. As it's a lesson on the limestone cycle. I'll start that again on the limestone cycle itself. Okay, so yeah, and here we have it again. Thermal decomposition, calcium carbonate, heat it, you get calcium oxide and you get carbon dioxide. And so the limestone cycle and the methane cycle are both part of the carbon cycle. And so the point is that the carbon cycle is concerned with the origin and fate of any compounds which contain carbon and how they move around the Earth. Okay, so all of the cycles, don't be thinking that these cycles are all disconnected from each other, because they're not. They're all interconnected with each other. It's about the movement of energy. It's about the movement of matter between systems, and those systems seek to balance themselves. In biology, you'll come across a word called homeostasis, and then which is about keeping processes within very, very precise limits. And it's the same with the Earth. If things get knocked out of balance, when an energy balance when things are knocked out, not in sync, when things aren't synchronized, the way the cycle, whatever cycle it is, the way that it works will change until a new balance is reached. And that's the thing with climate and with the greenhouse gases, because the emissions of greenhouse gases and the destruction of the natural world have unbalanced the carbon cycle. It's not in synchrony anymore. It's out of sync. We've put too much of it into the atmosphere, and we've created a situation is now created where it's got nowhere to go. So, and that's going to leads us on to the carbon dioxide concentrations in the atmosphere. This is pretty stark stuff. The flow of carbon dioxide through the carbon cycle has been in balance for millions of years. Over the last few hundred years, it's been disrupted. And you can see the numbers here. These are numbers actually come, and there's a hyperlink here, actually come from an observatory in Hawaii, I think it's in Hawaii, called Mauna Kea. And what it was set up in 1958, actually. And what they did was it's up there, and it just measures the concentration of gases in the atmosphere. It measures all of them, and the link there will show you where they all are. But it shows you in 1958 there were 315 parts per million. 2000 it was 380, and in 2022 it's about 400 parts per million, and it's going up like that. And it's not stopping. I'm sorry to say, it's not stopping. Yeah, so that's what the sort of trend is, and this is what it looks like in a graph. So you can see that the parts per million means it's about 420 up here, and we have here and the purple bit is parts per million, and the blue line is the emissions of CO2 emissions. You can see how the two are connected. And basically, what it says, what do you notice from here? What's the difference between, say, here? What's the difference, say, between this part and this part? Anybody?
I think the purple part is how much CO2 is in the atmosphere. And I think the blue part is how much CO2 is emitted into the atmosphere each year.
Mm-hmm. And also, if you can see, anybody out there, what about, and that's good, that's right, but what about the shape of the line? What do we see about the shape of the line? From about here, from about 1930, 1940, what's happened to the line, to both of them?
It decreases a little bit.
It's increased. It's gone up markedly straight after the Second World War. There was a massive after the Second World War. There was a massive spurt, if you like, of economic development in the Western world, and lots of economic activity around the world in general, and that was all based on fossil fuels. So there was a massive spike in emissions of CO2 and other gases into the atmosphere, and the environmental destruction as well. But the point is that levels haven't been this high for 800,000 years. We haven't even evolved then. Modern human beings, Homo sapiens, hadn't really appeared by then. So the point is now we're creating a set of circumstances that we haven't been evolved to live under. That's that always worried me. That did find out things like that always made me think, maybe we ought to do something about this, slow down and reflect on it, because this is how it works. I mean, you've probably seen graphs like this before. The sun shines on the Earth, and solar radiation comes through. It gets re-radiated back as heat to the Earth. And when it's supposed to, what it's supposed to do, most of it's supposed to go into space, but it doesn't. If you put greenhouse gases into the atmosphere, CO2, methane, and others, lots more of it gets trapped in the atmosphere, less heat escapes to space, and the atmosphere itself begins to heat up, which it's not supposed to do. And there's no limit here, because of the more greenhouse gases you put in, the more heat you're going to get in the atmosphere. And also, it has to be born in, better think about this one as well. The sun itself is what's called a main sequence star. And what those sorts of stars do is as they go through their life, they produce, they become brighter and hotter as they go through their lives. So what we've got here is a sun that's producing more heat and then an atmosphere on the Earth that's trapping more of it. But and so that's what's happening there. But the point as well, another thing to remember, is carbon dioxide in the atmosphere keeps the Earth much warmer than it should be. So we do need a little bit in there. That 0.03% that we mentioned, that needs to be there. Otherwise, the planet would be 30 degrees colder than it is. Life just wouldn't be possible. We wouldn't have any liquid water or liquid water. It would just be too cold, and which it was until life was able to come out of the ocean. So it's important to realize that carbon dioxide is important in the atmosphere. We do need a natural greenhouse effect. We don't need an unnatural one. Okay, so it's how it works. What's called shortwave radiation passes through the atmosphere. Some of this radiation is reflected back into space. And some of it, though, comes through, hits the ground, and is emitted back into the lower atmosphere, what's called the troposphere. Some infrared radiation is absorbed by the greenhouse gases. That's the GHGs, greenhouse gases. Like in the same way as a pane of glass absorbs infrared radiation in the greenhouses that we've got. We've got a greenhouse and a polytunnel, and we have materials in there that help it absorb the more heat to help the plants grow. And what happens is all the gases absorb this radiation and then they re-emit it as heat. So what we're happening here is, and this is this idea again, the greenhouse effect, the GHG, is the process, but climate change is the consequence. Okay, so this idea of processes, consequences, sinks, and sources is the basis of all of this. So what we're saying is, shortwave, ultraviolet radiation passes through the atmosphere. Some of that gets reflected back into space. When the ultraviolet radiation hits the ground, its wavelength changes. And when the wavelength changes in such a way, the greenhouse gases in the atmosphere absorb that infrared radiation, and then it gets re-emitted as heat into the atmosphere, warming the atmosphere, and so warming the planet more than it should do. So there they are. This is the main ones you're going to come across: nitrous oxide, carbon dioxide, and methane and water vapor. It's important to realize that carbon dioxide isn't the only greenhouse gas. We have, because there are these other gases as well. You'll sometimes see scientists speak about something called carbon equivalence. And then, so when we count in when this idea of carbon equivalence is added into the numbers about what we're looking at, what the parts per million of carbon dioxide is, some science at the lower end, when you put in carbon equivalent, CO2 equivalents in the atmosphere, the lower end of the science says that we're looking at 440 parts per million. The other upper end says it's about 500 parts per million. So it really does depend what we're looking at. But what we can say for sure is that we're definitely at 420 parts per million. We've never been this high before. It's never been, ever, for millions of years, that much carbon dioxide in the atmosphere. And this is just another slide here which shows which are the natural ones, which are the unnatural ones. So, excuse me. You would have heard of substances called CFCs, or halogenated hydrocarbons. They are most famous for the wrong reason of being very good at destroying the ozone layer, but they're also very, very good at absorbing greenhouse gases as well. So you've got all of these substances in the atmosphere, a brew, if you like, of different atoms, different molecules, sorry, in the atmosphere. All of them in their own way are good, are able to absorb infrared radiation and re-emit it as heat, and then heat the atmosphere, and so heat the rest of the planet. And they all do it to varying degrees, so which is why we have this idea of carbon equivalence. So yeah, so they're the main molecules that we need to know about when it comes to greenhouse gases in the atmosphere. Okay, and here's some more of them here. Here they are again, just represented differently. So the way, and all of the, you can see the bonds, the chemical bonds in all of these elements, molecules, sorry, compounds. They're able, because of the bonds, they're able to absorb specific wavelengths of light from the sun and then re-emit it as heat into the atmosphere. And if you're doing physics, especially if you're going to do physics at A level, you'll study in detail how that actually happens, what actually happens to the bonds and how they react when they're heated. So there's a link at the end of the presentation as well. Okay, okay, so beginning to wrap things up now. Greenhouse gases haven't been this high, 400, 500 parts per million, for 15 million years. 15 million years ago, temperatures were 3 to 5 degrees warmer than they are now. Sea levels were meters higher than they are now. And at the moment, carbon dioxide levels are increasing by 2 to 3 parts per million every year. By 2025, we're looking at being, if that's 3 years from now, we're looking at being 430 parts per million equivalents. And that means that the planet will be on average 2 degrees warmer than it should be. And by 2030, 2040, we will be at levels not on the current path, current trajectories will be at levels not seen for 15 to 20 million years. And so the consequences of that, yeah, are going to be interesting, to say the least. Yeah, I don't know if you've seen the news, but there's been a new report published this week, basically highlighting this, explaining this, and saying that by 2025 we have to reduce our emissions, and by 2030 we have to have our emissions reduced to 50% less than what they are at the moment. And if they're not, then we're going to be heading into, as I said, heading into this territory. And just, I hate to say it, it's actually quite frightening. Which is of course why I study it, why I look at it. Yeah. There we are. This is the point. This is the point we're looking at. It's another graph for you to look at. The red line shows the current trajectory of what we're doing, of gigatons of carbon into the atmosphere. If we want to stay below 2 degrees, we have to be here. And if we want to stay below 1.5 degrees, we have to be here. But of course, we're doing that. What about this gap? These gaps represent what we should be doing. We shouldn't be like that. That shouldn't be there. That needs to be there. The red line needs to come down here, like that. It needs to be underneath, certainly at least underneath this one. And because this graph shows how things are actually playing out. So what you notice that in the graph there, what you notice about the graph. Now the point is that those we've known this issue, this climate issue, the buildup of carbon dioxide in the atmosphere. We've known since the mid 1800s, since the Industrial Revolution, since the 1840s, that something might be up with this. It was confirmed definitely in the mid 1930s by some groundbreaking science from Germany, I believe. I believe Germany or Switzerland, from Europe anyway at the time, saying, look, this pumping of carbon dioxide into the atmosphere is having these problems. We need to do something about it. We've known it, so we've known for at least 80 years, or about 80 years, that something might be up. And there's been various speeches made in the United States and Russia and around the world saying we've got to do something about this. But it's obvious that nothing like enough is being done about it because of this line. It indicates completely that the current trajectory is going this way. It's going the complete opposite of what we should be doing. So that's where we are with emissions. I just thought I'd wrap up really with the last few slides here. I thought I'd show you, because you live on an island, I live on an island, so I thought I'd show you a quick couple of slides here about this island here, Madagascar, just outside of in the Indian Ocean. This year they've been hit by 4 tropical storms, cyclones that they call them, that they call there, and they're all climate related because the Indian Ocean is getting warmer. It's warmer than it should be. So there's 3 cyclones here that I've just put the hyperlinks into for you to have a look at. They've also had, all of the trees most of the forests have been destroyed anyway by deforestation, forest destruction in Madagascar. They've had lots of mining, and lots of environmental destruction has happened. No benefit at all to the people who live in the country. They've been left with nothing. And then this year they've been hit by cyclones and storms. And the consequence of it is there. That's the picture of the island in Madagascar. That's just and there's a link there that just shows a couple of links underneath which show what happens. So that's what happens when storms hit. It just destroys everything in their path. There's been floods and fires and all sorts of things happen. Disasters like that happen all over the world. And these links underneath is here. It's from an organization that I've been part of since it started, since it formed in the late 1990s. And there's a wealth of information in there about all of this. But that's what happens when the storms hit. Now, it's really important to understand, this is something I probably should have said earlier, is that climate change doesn't make the weather. It doesn't create the weather. It intensifies that which was already there. So there would have been a storm here already. The cyclones would have been here already. But they would not have been as powerful as they have been if we weren't in the situation that we're in as regards the Earth's climate. And there's another link there, so it's got more of a roundup of other things which have happened in the world as well. So that's what happened when the cyclone hit inside the island. That's a village somewhere that's been, obviously you can see that it's been destroyed. This is one of the main cities in the island that was hit by the same cyclone. This is a built-up area that was, I think it's part of the capital city, and you can see that the water has literally been dumped from the sea, been dumped internally in the island. So you can imagine it's like all of this has been flooded. So that's what it means when you have a climate-related event for that part of the world. in other parts of the world, there'll be different sorts of consequences. Yeah, so that's a link for it for the UN, for the United Nations. Okay, all right, there we are. There we go. There's the carbon cycle summarized. So where does it come from? These are the kinds of questions that we can ask ourselves. Where does it come from, the CO2? How is it stored? How is it used? How is it transported? Is it fixed? What processes drive the carbon cycle? And to sum it all up, where we should be, the figure we said at the beginning was 0.4%, but we should actually be 0.03%. Now that's 100 of 1%. Doesn't really sound a lot, but when you think about it in terms of what's going on in the whole planet and the way that this has been a constant cycle for millions of years, and the way that things that we've upset it by putting far too much carbon dioxide into the atmosphere, whilst at the same time ensuring that because we've destroyed all the forests, and we're still, or most of the forests, and other carbon sinks, and we're still combusting fossil fuels, making cement and such like, and other processes, we've now basically turned the atmosphere is now a source of carbon dioxide to the rest of the natural world, and it's got to go somewhere. And there we are. So there we are. The last couple of slides just have some links for you to have a look at. As I said, I wasn't quite sure what level I was going to be looking at, what kind of level I was going to be teaching or talking to you with. So I just thought I'd put this together, and I put these other links in for you to have a look at as well. Okay, that's an overview of carbon dioxide, and the carbon cycle. There we are. So, okay, any questions at all? Such like. Cool. I'll take that as a no then for the moment. Hello.
I was saying I didn't have any questions.
Okay, cool. Okay, all right. What we'll do then, I'll have a word with I'll talk to Miss Lewis on this, and what we'll probably get, we'll try and get you some sort of get you an activity to do on this in some way. Now, what happens in exams with this? What you'll normally be expected to do is you'll get given. Perhaps there won't be so many drawings on it, but what will happen when you get if you do it, if it comes up as a structured question, you'll be expected to know. You might have to write an equation for what's happening here, or for what's happening here. So you'll get given a picture or a diagram, like the ones that you've seen in here, and you'll be asked to explain what's going on with what the processes are. You might be asked to explain what a sink is, or what a source is of carbon to the atmosphere, and you might be asked to explain what's going on in the oceans, and things of that nature. So it's the kind of thing that will come up if it does in paper 2, which I think is your structured questions in chemistry. But yeah, okay, that's enough from me, I think. I hope you got something out of it. I hope you learned something. I've certainly enjoyed talking to you, or talking with you. Yeah. So yeah,
it was very informative, I must say.
Thank you. Thank you.
Excuse me.
Okay, so okay, Miss Lewis, are we finished now, or do you have anything to add?
Excuse me, Mr. Barr.
Okay, go ahead, Anaya.
I wanted to say that I knew about the Great Dying.
Yeah.
I wrote a report on it, and it's really interesting. And then the part where you said we're using up a lot of the heat from the sun. And I know that eventually they say that the sun's going to run out, and that people think that there's a blue star that they can use as like a new sun. I heard about that on Thought 2.
Yeah. I also have a look at astronomy as well sometimes. I mean, there's a fellow called Brian Cox. He talks about this all the time. The sun has got they reckon, the astronomers reckon, it's got about 4-5 billion years to go before it blows up and turns into a red giant. But they think that in about 2 billion years, it's going to be so hot, it's going to be producing so much heat that it's going to make life on Earth much more difficult than it is at the moment anyway, because it's going to make the planet too hot. So that, excuse me, that is is something to look at there. So it used to be the big blue stars. What do they call them? They're big, huge ones. What do they call them? Super giants, is it that they're called? Those ones?
Novas.
The what?
Nova star.
That's it. Yeah, I think that's what they're called. I'm not I'm not a professional astronomer, but I think that's what they're called. Those ones there. So yeah, the Great Dying though was definitely there. Was definitely something that's as I said, got me interested in all of this. It just made me think straight away about natural processes. It made me think about the power of the Earth, and it made me think about the importance of applying, if you like, some of the chemistry that you learn. I mean, because I said at the beginning that I did environmental science and environmental chemistry. We'd learn what the way that worked was that we'd learn, for instance, we'd learn how metal carbonates work and how they form and what they do. But then we'd also learn that how the reactions, some of the chemical equations that we've seen in here, how they would go with the rest of the world, how they actually apply and how they actually work in the real world. And so what actually happens when the place I did, as another example, the place that I studied at was a place called Plymouth, which is in the west of England, and there used to be a lot of mining there, like small tin mines and small metal mines. And what used to happen sometimes was if we got too much rain in the mines, what would happen is the water inside the mines is really, really acidic, and what would happen is it would wash through the mines, and what would happen is it would wash into like the estuaries or into the areas and the fresh water around. And because you'd have a change in the chemistry of the water, what would happen is you get lumps of metal, particles of metal would precipitate out of the water and fall in the earth. And we learned about when we learned formed it into the water, and we learned how changes in acidity can cause metals and other substances to come out of solution and become solid and fall as particles on the ground in the water. So yeah.
Thank you.
That's all right. Not at all. Not at all. Not at all. So anybody else? Any other questions from anyone else?
So they are saying that the sun will eventually dissolve.
The sun
will eventually dissolve.
The sun, it won't dissolve. It will blow up. It will become a red giant. What's called a red giant is what it's called. What it's going to do is the sun will. What happens is in a star, in the sun, like all stars, they basically what happens is you have. I'm doing this from memory. You have the fusion of hydrogen atoms in the sun makes helium. And what happens is like in a hydrogen bomb. And what happens is you just get huge amounts of energy released from hundreds of billions and billions and billions and billions and billions and billions and billions of individual atoms, all condensed into one place, at the center of the sun, inside the core, and there's huge nuclear reactions which happen and generates the heat. Eventually, what happens is the sun is going to run out of hydrogen, and then it's going to, when it does that, it begins to expand, and it turns into a red giant star. And what that will mean is at the time when it does that, about 4.5 billion years from now, so we don't have to worry yet. Whoever's alive at the time might have to, but we don't. By then maybe we'll be traveling through space or something, who knows. But what happens is by the time the sun becomes a red giant, its size will mean it will be big enough to swallow up the Earth. It will be the size of the orbit of the Earth at least. And they think what will happen is that perhaps it will kickstart life on some of the gas giant planets that there are. We don't know, but we won't be here to see that. But that's what will happen to the sun.
Yes, sir.
Thank you very much.
That's all right. That's all right. I hope to see you again. Because I've not, as I said, I've been working with Miss Lewis since 2013 or so, and we both of us are excited about getting the student shed up and running again. It's part of the reason, well, it's the reason why I wanted to do this session as quickly as possible. I really hope you got something out of it. I believe that it's being recorded. You'll have the PDF to look at as well. Yeah, I hope you got something out of that. I hope you learned something. And maybe what we could do is perhaps do something about what's being done about all of the processes that we've been talking about, because it's not all doom and gloom. We need to fix it. We really do need to fix it, and we are running out of time. But there are solutions to this. There are things that can be done. The point is that they're not being done. And maybe in the future we can look at some of the reasons why they're not being done and what can be done to make things get done to solve all of this, because this is about the future of life on Earth and yourselves as well. I mean, I'm 51 years old, so by the time it gets to 2030, 2040, I'm going to be in my 70s. I'm going to be old, really old. I think I'm old now. I'm going to be even older by then. You yourselves won't be. Some of you are going to be, if you're in sort of grade 10, grade 6 or such like, you're going to be, late 20s, mid 30s. You're going to be living in this. You know, you're going to be in the prime of your lives, as it were. So it would be nice to have to sort it, to stop it, because, as I said, they've known about this for a long, long time, and nothing's been done about it. And there's the reasons why nothing's been done about it, which for me is, you know, it's incredible for all the wrong reasons. Okay.
Yes, sir.
So yeah, I hope to see you all again soon. Are we finished, Miss Lewis? Do you want to talk to me afterwards, or?
All right. Yes, we're done. Okay. Thank
Okay,
you
cool.
so much, Mark. And thank you guys for showing up and taking this time out with us.
Yeah,
like Mark
great.
said, we'll get the PDF to you, the slides to you, and the recording as well. So thank you all again, and we'll see you all
And
next
have
time.
Thank you very much.
So, okay, that's us finished there. Thank you very much, as I said, for coming. Right then. Okay, good night, everybody.
All right.
Good.
Good night, everyone.
Night, night.